Hello everyone. In this video, we will talk about equilibrium of a rigid body. Now, from the previous videos, we transitioned from a particle to a body. So here we have a picture of a rigid body with several forces distributed on it, and let's call the point O here the center of gravity. Now, for this body to be in equilibrium, the resultant force of all of the forces, so F1, F2, etc. So the resultant is the sum of all the forces and has to equal zero. So this has to be valid for the particle to be in equilibrium. And the same thing, the moment of these forces around point O is the sum of the moment of each force, and this has to also equal zero. So we have this also. And so let's say, so now we have the moment about O. We want to know what's the sum of the moment about point A. Now let's call the directional vector R from A to O as such. And the sum of the moment of A is just basically R cross product. Now remember we covered before the cross product and we covered how we do the moment. Plus MRO equals 0. Now if you look at this carefully, what is MRO? If we go back to this equation, if we go back to that equation, MRO is 0. So this is 0. Thus, sum of the moment about A is just the R vector cross product with FR. Now this is only valid if the rigid body is in equilibrium, otherwise MRO has an actual value. Now moving on. So the equation of equilibrium for a rigid body are basically the same as those of a particle. We have the sum of the forces is equal to 0 and the sum of the moment equal to 0. Now if we're doing it in 3D, we have sum of forces in x equals 0, sum of the forces in y equals 0, same thing for z, and the sum of the moment O is 0. Now notice this is basically a repetition of what we covered before. Now let's do maybe a quick example about this to kind of get the idea a bit more clear. So let's say we have this body here, pin A. Now notice pin A is free to move in the x direction, and pin B, we have a force 600 Newton at 45 degrees, and these are the dimensions: force 100 Newton, 200 Newtons. So we want to know what are the reactions, A, AY, BY, and BX. So basically, we can first start by doing the sum of the forces in the x direction. So what do we have? We have 600 cosine theta. We have, and Bx. Those are the only two forces, so we can easily get Bx. And now, to get Ay, we can do the sum of the moment about point B. So we have the force 100 times 2 plus the 600 cosine 45 times this 0.2, and we have the reaction AY times the total distance, which is 2 plus 3 plus 2, which is 7, and this is the number over here. So if we solve this equation, we get AY to be 390 newtons. Now the last step to get for the B reaction in the Y direction, we can do the sum of the forces in the Y. So we have AY, which is 319, 600 sine 45, that's this force over here, and we have minus 100, minus 200, that's another external force over here, and plus By equals 0, and we get finally By is 405 newtons. Now the final thing I want to talk about is 2 force member and 3 force member. So let's say we have a link like this, For this link to be, let's say we have two forces at the end, F1 and F2. Now for this rigid body to be in equilibrium, F1 and F2 have to be in the same direction, but in the same alignment, but opposite directions. So if we look at it over here, otherwise if we have F1 like this and F2 like this, the body can be rotating in this direction or in this direction depending on the magnitude. So again, this can help you if you're solving a problem with only two forces. You know directly that they have to be aligned. Now if a member has three forces on it, if we extend all of the direction, they have to meet at one point, and this will be this is the point of equilibrium. So let's say, for example, if we have this sort of member, F1 like this, F2, let's call this F1, F2, and F3. Now if we extend this, we notice we have more than one point, thus this member is not in equilibrium. Now, this basically gives also an introduction about rigid bodies. We will go over more in depth about this in future chapters. Thank you everyone for listening.